Hi guys, my name is Ben, and Ella let me present on our senior design project, really knocking out two birds with one stone here. Let's get into it. So the background for our project, 2 years ago in 2023, Lost Space sponsored a senior design project to make a rover. Last year, they sponsored a team to make a solar panel to put on that rover, and this year, they sponsored us to put a drone on top of that rover. They gave us a few specific requirements. It's got to be able to fly for 3 hours. It's got to be able to record video data, with the real intention being that the drone's up in the air recording video data of the landscape that the rover couldn't get from a ground view. And then lastly, it has to transmit that data to the rover to be effective. We also had some optional requirements, which is wireless data transmission, so it can actively transmit that data while it's flying around. A detachable tether, so you could have a short period of longer range, because the drone's primarily getting power for the whole duration by tethering to the rover's battery. Otherwise, you wouldn't be able to get up to 3 hour flight times. So a detachable tether gives you like 20 minutes of extended range. Also a spool-based cable management system. This is because if there's a lot of tether, you need to be able to manage all of that, so a spool to do that. Lastly, a magnetic docking system to keep the drone in place on the rover while the rover is driving around so it doesn't fall off. I'm just gonna give you, not gonna go through all the concept selection because most of this is electronics and that's gross. So I'm just gonna show you briefly. The big one is we're using this drone kit over here for our drone. There's a rover platform stuff which is gonna be made out of aluminum, which we care about. The rest of this just could not care less. Really what I want to talk about with this presentation is some of the engineering analysis considerations with this, because I could go over concept selection, but I don't think that really is that relevant to you guys. So one of the main considerations is the weight on the drone. If we need a 3 hour flight time, that's a directly proportional to the weight that the drone can carry. If we make it super heavy, it's not gonna have a long flight time. What you see here are some equations. This one over here is how you calculate thrust on a drone. This one over here is the thrust coefficient in that equation. As you can see, that's a nightmare. So I have all of these values over here. Most of them are just factors that they generally tell you, hey, assume this for this factor, this for that factor. If you're going really in depth, you can come up with each one. Important ones are your BP, that's your blade pitch. BP is your blade count, HP is your blade pitch. So we have four propellers with a 0.11 meter thing. It looks weird because it's in inches, not meters typically. And then down here for the main equation, you get air density, which is actually not constant. It's a function changing with your height. We use a constant value though, just for this estimate. N is your RPM of your motors, and DP is the length of your blades. So these are 10-inch propellers, but they come out to meters for this calculation. All of that fun math, you do it, and you come out with 27 newtons of thrust generated by the propellers. This means if we add some contingency, so we're not going at max power, we get 24 newtons available, which gives us 22.47 kilograms of weight budget. All that to say, we can have about 0.8 kilograms of tether length or additional electronics on board. This matters because it directly says how long our tether can be. We were initially shooting for a 10-meter tether. After doing all this math and finding out our tether geometry, we can have a 80-meter tether, which is much longer. We could actually, we're gonna see on the next slide, you can take that equation and you can come up with different thrusts based on propeller length, because you could do it with motors as well, but it's very cost inefficient. We could get all the way up to 111 newtons of thrust and get a crazy long tether, but you actually are not, that's not legal due to the FAA code. So we modeled all of this, or made a graph out of all of this just to kind of see if there's any outliers. The thrust versus dollars was just to really see if there's any cost efficient options, which they're all generally around the same. And then we can see just how many newtons of thrust we want based on a cost. We can't really just pick and choose anywhere on here because each motor is rated for a certain propeller. Because as you can imagine, if you have an 8-inch propeller versus a 16-inch propeller, one's going to be twice as heavy, and then the motor's going to have to work twice as hard to spin it. So they're rated for torques. For the motors we're using, we were rated up to 12 inches of propeller length. We're going to end up, get 10 comes with our kit, but it's only $20 to buy some 11-inch propellers, so we're going to do that to get a longer tether length. But lastly, and the most fun calculation, doesn't look like a lot, but I promise it's not great, is the slack in the line. As you can imagine, this drone is going to be off somewhere far away, and there you can approximate the distance of the tether by a straight line distance from the center of the rover all the way up to the drone up here. However, if you've ever seen any cables in the air, they're not taut. There's some slack in the line. This is due to the weight of the tether itself, as well as the way you want to actuate the drone. You don't want it to be taut, otherwise it might be tugging on it as it flies, which isn't a good idea. So how do you measure how much slack is in the line? It's a great question that I wish one of you could have answered before I did all this, but it's through a catenary curve. It's the natural curve between two endpoints of a tether. And you get these really complicated equations where L is the total length of the tether and Y is the height of the tether. We have to use R because we're in three-dimensional space, which dimensionalizes X and Z together. And then C and L are just two unknowns, L being our length and C being a constant. A is a measurement of H over W, W being the sag, or the unit per, or weight per unit length in the line, so how heavy your tether is pretty much. And H is tension in the line, which you can kind of decide to be whatever you want. For us though, it's pretty relevant to use drag force to approximate H because you can put a wind velocity in here, and then you can come up with some wind resistance, which is a metric important to drones. Each drone is rated to some wind resistance, so if we can set this wind resistance equal to the wind resistance of our drone, we can maximize our functionality without having to reduce anything. You put all that together into MATLAB, and you solve it, and you get that your tether length can be this long for this wind resistance. After doing all of that and putting it into MATLAB, it turned out with some really weird results. And then a lot of research later found out that this model actually is not effective for super light tethers. Our tether is 6 grams per meter, which is really, really light. And it just straight up doesn't work for these approximations. And then you look up more options and nothing works for those weights of tethers. So we're gonna actually have to go back and test over and over different tether lengths, see what the slack looks like in the line to come up with an actual answer, but this is as far as the math can get you. So if we used I think we're ending up using a high voltage line. I'm not gonna go deep into electronics. High voltage line because it's really light. If you used a low voltage line, you could use a method like this, but this was done before we decided on a high voltage line. But those were like the big 3 mechanical engineering analysis I wanted to go over. There's giving a 30-minute presentation on it next Monday. Didn't want to, go over way too much stuff, but that's all I have in consideration of that. If there's any questions of parts of the project you guys are interested in hearing about, I can go over that, but otherwise, that's what I have.
Super cool project.